In this video, we will do a Lagrange multipliers example where we find the max and min values of a function given some constraint where there are three variables. All right, so the example says, let's find the maximum and minimum values of f of x comma y comma z equals x squared plus x plus 3y squared plus 2z squared given x squared plus y squared plus z squared equals 1. Okay, so I noticed that the function f is the function that I want to find the max and min values of, and this other equation is our constraint. So with the constraint, I want to rearrange it to get everything on one side. X squared plus y squared plus z squared minus 1 equals 0. And when I do that, the function that I have on this left-hand side, that is what we call g. All right, so now we are ready to construct our Lagrangian. So construct our Lagrangian function, which we've been calling L. And this time L is going to be in terms of three variables, x comma y comma z. And the Lagrangian starts with f, and then you do minus lambda times g. So f is x squared plus x plus 3y squared plus 2z squared. And then we get minus lambda times g, x squared plus y squared plus z squared minus 1. All right, so we have our Lagrangian. Now we are ready to find the critical points of this. All right, so we need to take some partial derivatives of this and set them equal to 0. So we'll need to take the partial with respect to x, set that equal to 0, partial with respect to y, and the partial with respect to z, set those all equal to 0. Okay, so before doing that, let's distribute this minus lambda into the terms of g. That would give us minus lambda x squared minus lambda y squared minus lambda z squared, and then plus lambda. And now let's take these partials. So when I take the partial with respect to x, from the terms that are in the function f, we'll get 2x plus 1. And then when I take the partial with respect to x of the terms that are in the minus lambda g, we'll end up with minus 2 lambda x. Okay, that equals 0. All right, so now partial with respect to y. So when I do that for the terms in the function f, we get 6y. And for the terms in minus lambda g, we will get minus 2 lambda y. And that is equal to 0. And then finally, for the partial with respect to z, from the terms in the function f, that partial is 4z. And for the terms that are in minus lambda g, that partial will be minus 2 lambda z. And I set that equal to 0. Okay, so we have 1, 2, and 3 equations, but there's 4 unknowns, x, y, z, and lambda. So we are going to need that extra equation, which when we do Lagrange multipliers is our constraint, which was x squared plus y squared plus z squared equals 1. So we get to our system of equations. This is typically one of the more challenging parts of a Lagrange problem, navigating these systems of equations. So I want you to try this on your own first. Pause the video for about 4 minutes. Really pause the video for about 4 minutes and see if you can make progress with solving this equation. 4, 3, 2, 1. Pause that video. Pause it for about 4 minutes and see if you can make progress with solving this equation. That may not be enough time to finish the whole system, but hopefully to make some good progress with it. All right, so hopefully you've done that. Hopefully pause the video for about 4 minutes to really try solving this system. There's usually more than one way to go, but often what we do is we focus on one of the simpler looking equations. So I noticed, for example, that equations 2 and equation 3 both just have 2 terms on the left-hand side, whereas equation 1 has 3 terms on the left-hand side. So maybe I'll start with either equation 2 or equation 3. So for example, if I started with the equation 2 this time, notice that we can factor out 2y. Now let's put that in black actually. We can factor out a 2y and be left with 3 minus lambda, and that equals 0. And remember, I would not want to divide both sides of that equation by y. If we divide and cancel away a variable, you can lose solutions. All right, so that is really important. All right, so from our factorization here, from the first factor, the 2y, we would get y equals 0. And from the other factor, the 3 minus lambda, we get that lambda is equal to 3. We get these two possibilities. Okay, so now we're going to have to work with these two different possibilities. So first, let's do the case where y equals 0. All right, so I know y equals 0 in this first case, and I'm going to now have to work with one of the other equations. So if I were to work with the third equation, we notice that one was kind of simple-ish as well. Just like the second equation in that it had two terms and we could factor a little bit. We could factor out a 2z and be left with 2 minus lambda equals 0. And what that will tell me is, so if I write that down here, from that third equation, we know from that factored form that z equals 0 or lambda equals 2. So we know that either z equals 0 or lambda equals 2. So let's deal with each of these. So first let's do z equals 0. So we're working within the case where y equals 0. And now if we also are looking at the case where z equals 0, we could plug into the fourth equation, our constraint, to get that x squared plus 0 squared for y squared plus 0 squared for z squared equals 1. And if I simplify this, we get x equals plus or minus 1. All right, so when z equals 0, we know the possible values of x. And at the start of this, we had what y was equal to. So at this point, we have the values of all of our variables. But now I got to move on to this other situation, which is, well, what if instead of z being equal to 0, what if I just know that lambda equals 2? So where could I plug that value in? So this maybe I could plug into equation 1. And if I did that, we would end up with 2x plus 1 minus 2 times lambda, which is 2. X equals 0. I'm going to put a little line there so I can separate my work. We are dealing with subcases here, so really got to organize my work, right? Because initially we had the two cases, y equals 0 or lambda equals 3. So far we were just looking at the case where y equals 0, and within that case we've broken it up into a couple of subcases. One possibility was where z equals 0, we worked that one out. And the other possibility we're looking at now is when lambda equals 2, and we're in the process of working that one out. All right, so let's simplify this more. If I leave the 1 where it is, I get also with it 2x minus 4x, which is negative 2x. Let's move that to the right. So we get 1 equals 2x. And if I divide by 2, we get 1/2 equals x. So now we know the y value, it was 0, and I know the x value, 1/2. So we can plug these in to our constraint to get 1/2 squared plus y squared was 0 squared, and then plus z squared equals 1. And if we simplify this, we end up with z squared is going to be 1 minus 1/4, which is 3/4. So if I square root both sides, we get z equals plus or minus. On the top, I get root 3 when I square root it. On the bottom, square root of 4 is going to be 2. So we get z equals plus or minus root 3 over 2. All right, so we have finished this subcase when lambda equals 2. All right, so now we got to go back. We got to back it up. We've finished the y equals 0 case. Now let's move on to the lambda equals 3 case. So just like we did before, I know from the third equation, which we factored up here, 2z times 2 minus lambda equals 0, we're going to get z equals 0 or lambda equals 2. we're going to get these two subcases. So lambda equals 2 is actually going to be impossible in this case, because we're looking at the case where lambda equals 3. And if lambda equals 3, it's impossible for lambda to also be equal to 2. So this is impossible if lambda also is 3. Okay, so that cuts down my work a little bit. Lambda can't be 3 and 2 at the same time, so I'm not going to get anything from when lambda equals 2. But from when z equals 0, that one, I will have to do a little bit. So when z equals 0, now we know that lambda equals 3 and z equals 0 within this subcase. So I could take that lambda value and plug it into my first equation and get 2x plus 1 minus 2 times lambda, which is 3, x equals 0. And if I simplify this, we get 1 equals 4x. Dividing by 4, we get 1/4 equals x. All right, so now I know the z value, which is 0, and the x value, which is 1/4. So I can plug into my constraint to get 1/4 squared plus y squared plus 0 squared for z squared equals 1. And if I simplify this, we get y squared equals 15 over 16. If I do 1 minus the 1/4 squared term, 15 over 16. And if I square root this, we get y equals plus or minus, on the numerator I get square root of 15. And denominator square root of 16 is 4. All right, so we have worked out both of these cases when y equals 0 and when lambda equals 3. In general, the more variables that we have when we do these Lagrange problems, the more cases that we can run into, especially when it gets into situations where we factor to solve our equations. But we've systematically solved each of them. So let's just recap what our critical points were. So we had plus or minus 1, 0, 0. Right, so those were coming from this situation when y equals 0, z equals 0, and x equaled plus or minus 1/2. In the next subcase, we got x was 1/2, y was 0 again, and z was equal to plus or minus root 3 over 2. So writing that down, x was 1/2, y was 0, z was plus or minus root 3 over 2. And there's a few more. Okay, we also had, in the other scenario, when lambda equals 3, we got z equals 0, x was 1/4, and y was plus or minus this root 15 over 4. So writing that down, x is 1/4, y is plus or minus root 15 over 4, and z was 0. So altogether, we actually have 6 critical points. Okay, so sometimes to organize my work, when I have a lot of critical points to plug into my function, I'll make a table of values. In this case, I need to plug in an x, a y, and a z value into our function f. Okay, so the first 2 critical points had x is 0, x is 1 or -1, and the y value is 0 and z value is 0. Okay, so we get those. For the next critical points, we get x is 1/2, y is 0, z is root 3 over 2, or we could have 1/2, 0, and negative root 3 over 2. And for the final 2 critical points, x is 1/4, y could be positive root 15 over 4, 0, 0, or we could have 1/4 negative root 15 over 4, and then 0 for z. Okay, so I've gone through the process of already plugging all of these into our original function f, so I'm just going to tell you what we get when I plug each of these in. So from the first critical point, I get 1. The next one, I get 0. The next 2, I get the same thing. I get 9/4. And for the last 2, I also get the same thing, which is 25/8. 25/8. So now we're ready to write down our max and min values. So the max value is the largest output that we see here. which is the 25 over 8. That is the max. 25 over 8. This question just asked me for the value, which means just tell me the output. If I needed to also write down the points where it happened, I would have written something like, it occurs at 1/4, comma, plus or minus root 15 over 4, comma 0, if I needed to. All right, let's do the min value. The min value, the smallest possible output that we got was 0. And that just occurred at one point. So if I needed to write it out, I would write something like, it occurs at -1, comma 0, comma 0.